We are discussing about stereogeometry, and we discussed how a fundamental matrix of this geometry characterizes the system. In this lecture, we will consider how to estimate a fundamental matrix given a pair of images of a stereo imaging system. So, you consider the relationships with the corresponding pairs of points for a fundamental matrix, and as we have already discussed that you have two pair of points, that is x prime, that is in the right stereo image, and x in the left, which is a reference stereo image. Then the relationships with the fundamental matrix between and also this pair of points can be described in this form, that is x prime transpose f x. Just to remind you that if I consider two images of a stereo system, as I mentioned, and consider a point, this is x, this is the reference camera system or reference image plane of the stereo system, and its corresponding point x prime. Now, the task of a fundamental matrix, or the property of a fundamental matrix is that it transforms a point into the epipolar line. So, it transforms a point. If I apply f x, it will transform, it will give me the line where x prime will occur. So, this line is given by this equation f x, and the applying the point content relationship of projective space, since x prime lies on this line. So, x prime transpose f x, that should be equal to 0. So, that is how we have derived this relationship. So, now we will see that using this property, how we can estimate a fundamental matrix given a pair of image points. So, for that we need to know, say, a few corresponding pairs of points. So, this is the problem now. So, this is the expansion of this particular equation. If I consider the element of the fundamental matrix is given in this form, it is a matrix element, and using the notation of indexing notations of an element of a matrix, that element of an ith row and jth column is given by f I j, and also you consider the column vector notation of a point. For example, x prime is given by x prime y prime 1. In our convention, we consider a point x prime, but its x coordinate is also denoted by this symbol x prime. Only thing is that it is a scalar quantity of an x coordinate, then y coordinate and 1. So, this is the representation of the point x prime there. So, if we can write it in this form, x prime y prime 1, that is what is x prime transpose, this is what is x prime transpose, and then multiply with fundamental matrix F, and also the point x in the reference image corresponding point, which is also given by this column vector x y 1. So, now you consider multiplications of these matrices. If you expand, you will get this equation. So, that is how this equation is derived. And again it would be convenient for us to represent in the form of a matrix, because in that case a set of linear equations can be represented by the matrix operations. So, a single equation is given in this way, and in the matrix notation here our objective is to compute the elements of fundamental matrix. So, these are unknown variables or unknown parameters in our case, and given the observation, these values we already know, because that is what is given to you. I mean, we will discuss later on how we can also compute these corresponding pairs in my next topic, but for the time being, let us assume that these points are given to you. Maybe even through manual observation in a crude way, you can get a few such matching points. So, these values are given to you, that means these coordinates are given to you. So, now this equation in the matrix form is written here. Let me write it in a proper notation, which is more convenient to understand. So, we will see that these are the coefficients of those equations. So, this is x dash x, x dash y, x prime, then y prime x, y prime y, y prime x, y 1. So, I am converting this equation in the matrix form, which is written here also. So, because this is for the sake of convenience, a column vector in this slide is shown by a row vector by using transpose operation. So, you are computing all these elements of fundamental matrix. So, you can see that all the rows are again represented as a column vector, and they are concatenated in this form. So, you have this F21, F22, F23, similarly F31, F32, F33. So, let me write. So, this is the matrix multiplication of that equation in the matrix representation, that is equal to 0. So, this is given, this equation is formed with only one pair of corresponding points, as I explained. Suppose you know a few more points. So, that means I can represent all these equations in a general matrix form. So, all the coefficients of those equations will come in this matrix. So, this is for the first pair of points. For the next pair of points, once again I will put these elements, observations, and I can write this equation. So, in this way, if I know n pair of points, n pairs of points, each one will give me one equation. So, as you can see, what is the number of columns in this case? You have here 9 unknowns, because fundamental matrix, the dimension is 3 cross 3. So, there are 9 unknowns. So, in this form we have I mean there are 9 columns and number of rows would be n, and there are 9 columns. So, this vector, let me write it, this is as a column vector f, and this matrix, let me write it as an A. So, A into f, that would be 0. So, 0 is also a column vector, because each equation is giving me 0. So, if there are n equations, so 0 will be a column vector of dimension n cross 1, and as we know, this should be 9 cross 1 and this dimension should be n cross 9. So, given n pairs of points, corresponding points, you can form this set of equations. So, now your task would be to solve this equation to get f, and you can see this is a homogeneous equation, a set of homogeneous equations. Again, you can apply the least square error estimate to solve this. However, you can make this equation as a non-homogeneous set. Suppose I consider I set this f33 value equal to 1, like we did earlier also. So, one of the value let us consider set to certain particular value, because I mentioned that though there are 9 elements, number of independent parameters in a fundamental matrix is 7. First thing, that it is a element of a projective space. So, if I multiply all the elements by a constant k, still this relationships it holds. That means, that is also a solution of this system. So, fundamental matrix multiplied by any scalar constant, they are all equivalent, that we discussed earlier. So, one of the element could be considered as a scale factor. Say, if I take this equal to 1, then this would be taken care of. So, in proportion to that value, all other values are expressed. That is one particular feature, property, so that it is at least one reduction of the number of independent parameters. The other constraint in a fundamental matrix that we also discussed, that it is a singular matrix. So, if I take the determinant of this matrix, it will be 0. So, you will get another equation. So, if I expand determinants, you will get equations in terms of all these elements, and that should be equal to 0. So, that is another constraint. So, that is why there are number of independent parameters 7. Now, for the time being, let us consider that we will be solving for 8 parameters. We will later on we will see that how that properties of singularity could be enforced. For the time being, let us approximately estimate fundamental matrix where this singularity constraint is waived. So, in that case, as I mentioned, that one of the parameter you can set to some known value, some given value. So, let us set to this value 1, and then again you convert this equation in this form. So, let me rub this part. So, once again, so if I can write this equation as x dash x f11 plus x prime y f12. So, these are the coefficients like this, all these values, and then y f32 equals minus f33. So, this is the equation, and that is set to 1. You know this equation. So, now once again you have a different matrix where your unknowns span from f11 to f32, and these elements, it is x dash x prime x, x prime y, like this it goes till this term y f32, and that is equal to minus f33. So, this is a transformation of this. So, now this equation becomes non-homogeneous equation, because this part is not 0, and in this way same for all the n corresponding pairs, you can get n such equations. So, let me consider that matrix, say A prime matrix. So, A prime into, let me use also A prime, these are the dimensionally reduced matrices because of this conversion, that should be equal to minus f33. For example, if I set set f33 equal to 1. So, this is the equation we will get. Actually, we will get a column vector of -1, because every equation will have -1. So, the dimension of this should be n cross 8. For dimension of this vector would be 8 cross 1, because there are 8 unknowns, and this is n cross 1. So, applying the solution for system of non-homogeneous equations, you can perform the least square estimate, and you know that if I consider this column vector as say b. So, I would be solving A f equals b, and since there are more number of equations, and usually you should have more number of equations, at least minimally you require 8 equations to solve it, then exactly you get a solution, because this matrix would be 8 cross 8, and if it is not a singular matrix, you perform inverse A inverse B, that would give you. So, when just you have 8 corresponding pairs of points, I can simply write f is A inverse B. So, that would be the solution in that case, and that is the requirement. You should have 8 numbers of corresponding points, that is the minimum requirement. And when it is n greater than 8, then what you need to do? You need to perform a least square estimate. That means, you will have to minimize the error. So, error is defined in this. So, these are the deviation of the vector b from vector A f. You can find out that this dimension of A f would be also n cross 1, and b would be n cross 1. So, if I take the norm of this vector, which is nothing but the sum of the square of its elements, and you can take the square root also, or sum of the square of its elements, and that should be I mean you can use also square just to show that square of the norm, that should be equal to, that you have to minimize this. So, you have to find out that f which will minimize this norm, and that can be solved by least square error method. There is a nice derivation we can perform by applying almost like matrix operations, but we can also we should use the theory of minimization in this case by taking the derivatives of this expression and equating it with 0. You have to solve these equations, then you will get these solutions. Just for the sake of your easily remembering particularly this aspect, what you can consider that you multiply transpose of A both the sides. So, you multiply this. So, now you see that this becomes a square matrix. So, this square matrix is in the form of 8 cross 8. A is n cross 8. So, A transpose is 8 cross n into n cross 8, and of course, the whole thing, this will be 8 cross 1. So, the solution of f tilde is A transpose A inverse A transpose B. So, this is your least square error solution. That is for the set of non-homogeneous equations. So, let me summarize these expressions, because I have also the slide set for this representation. So, as I mentioned, this is how we represent the system of equations given n pairs of corresponding points, and in our discussion we also mentioned that the elements of f, they can be retrieved up to scale. That means, whatever solution you get, if you multiply by any scalar constant, that would be also a solution of these equations. And also we discussed how minimum 8-point correspondences are required. There is a technique which we will discuss later on, that even you can do it 7-point correspondences, just to mention that, because as I mentioned there are 7 independent parameters. So, we will discuss this technique in my next slides. So, this is a representation of the set of equations with n pairs of corresponding points, and you can see this is that matrix A I was referring at. So, this is matrix A and this is the F, that is the column vector of consisting of elements of fundamental matrix, that is the unknown, and this is a set of equations. One of the problem with these representation is that the coordinates of these points, they have a very large range, and as you are taking products, in some cases you understand product of two large numbers will be also very large. So, the dynamic range of these coefficients of this equation of the unknown parameters, that widely vary. You can see that for the products, the ranges could be in the tune of in the tune of 10,000, this could be magnitudes, that is the variation ranges. It could be negative, positive, whatever, because the coordinates could be, usually in the images all the coordinates are positive. So, let us assume all values are positive. So, this is the range 10,000, 10,000, and whereas the coefficients with single variables range would be smaller, 100, assuming the images dimensions are in that hundreds only. So, 100 cross 100 image, but then you get all the coordinates within 100. So, that is why, since the orders of magnitude difference, it is a there is a lot of difference in that orders of magnitude. So, numerical stability is less in these computations, and it yields poor results. So, we will see how to handle that part. Let us proceed. So, one of the technique to take care of this particular fact, that why do not you transform the coordinates within a smaller within this unit range of -1 to 1. Then you can see even the products of coordinates also, they have equal ranges of the range of the single coordinates, all the coefficients they will have this. So, one of the technique is that you can transform these coordinates between -1 to 1 cross -1 to 1. That means, suppose you have your image coordinates, it varies. If I assume, say this is 0 0 and say this is the width and height of the image, say x max, y max. So, these are the coordinates within these ranges, all the coordinates are represented. So, now I would like to transform this coordinate, so that this becomes -1 1 and this becomes also, so sorry, this is -1 -1 and this becomes 1, 1. So, the variations are there. That means, exactly in the middle you have the center point is represented by origin 0, 0. So, this is how coordinate is transformed, and you can see that with transformations you get transformations in both the images independently, still you can recover the fundamental matrix. That also let us understand. Say you have an image, as I mentioned, say any point x, now it is transformed to a point. This transformation is given by this in the say left image, that means the reference image. For the right image, let us consider that another transformation we are performing. So, we are expressing in this. So, these are linear transformations. So, let me write it as T x and let me write it as also T x prime. So, if I consider the equation of the fundamental matrix involving fundamental matrix, so this is the equation that we are getting. So, now you consider apply this transformation. So, this is T prime. So, T prime x prime transpose f, and this is T x. So, what I will do, I will rather write transformed point. If the transformed point is y, so I will have y equals T x and y prime equals T prime x prime. So, x equals T inverse y. So, this is a requirement that transformation should be invertible, and x prime is T prime inverse y prime. So, now this should be written. So, now x prime is written as T prime inverse y prime transpose f, and x is T inverse y, that is equals 0. And performing this matrix transposition operation. So, y prime transpose T prime minus 1 transpose, then f, that is T prime inverse transpose. We can write it also T prime minus T in our previous notation, T inverse y equals 0. Now, you can see this is also a 3 cross 3 matrix, and this is a transformed matrix. After transformation, you get this matrix, you get this one. So, this is the fundamental matrix associated with y transformed points. So, what you can do? You can compute the fundamental matrix between this by using these transformed points, corresponding transformed points, where all these coordinates in these ranges will be used, and then from f tilde, from this whatever you get, then again transform it back to get the fundamental matrix, to get the original fundamental matrix. That relationship also we can use. Say this is T prime transpose, then f T inverse equals f tilde. So, now we will multiply at the both ends. So, both end we will multiply with T. So, it become identity, and in this case it would be T prime transpose. Okay. So, that would be equal to f. So, this is how you can get back the original fundamental matrix. So, with this let me stop here. We will continue this discussion of estimation of fundamental matrix in my next lecture. Thank you very much.